Okay, so welcome back to another video. So in today's video we have the following calculation we like to verify. The Riemann zeta of 2, which is equal to the infinite sum of 1 divided by n squared, I should have wrote this out even further, is that it's equal to pi squared divided by 2. And this is known as Basel's problem, which is it's a well-known problem in the world of mathematical analysis that was first proposed by mathematician Pietro Mengoli in 1650, and eventually it was solved by Leonard Euler in 1734. So it wouldn't be a problem if it has some application. Specifically, the solution itself actually calculates the probability, to estimate the probability that the two large random numbers are relatively prime. Okay, and so the way we're going to tackle this is we're going to be using Euler's approach. Really, it says that he actually used the series representation of sine of x and then just working from there. I don't want to give too much because that just ruins the surprise. Another neat thing to see is that with the Riemann zeta function itself, if you actually, you can actually prove the convergence of this using the integral test and see that with the inequalities, once you solve from there, that it creates this upper bound too. And another neat thing is that because this is an infinite sum that actually contains no negative terms, it actually has to converge strictly between 0 and 2. So that's actually neat. You can actually this is also interesting that Riemann zeta function of 2, it can be expressed, it can be expressed in terms of the Bernoulli's numbers, and there's actually a couple ways to prove this. I'm not going to go over them, I'll actually just say them, and if you want to read a little more about it, I'll leave it in the link in the description below the Wikipedia page. But there's also, you can actually prove this by using, they're all rigorous proofs really, so you can use Euler's formula and L'Hopital's formula. You can actually prove this using Fourier series, Parseval's identity, and Cauchy even proved this on his own as well. So that's another interesting way to approach it and then solve for the value of pi squared divided by 2. But and another thing with Euler's approach is that it has some generalization using the the elementary symmetric polynomials. It gives a little bit more generalization, even including Bernoulli's numbers included as well. But anyway, we're going to solve using Euler's method, series representation. We're just going to work from there, and then, all right, let's actually just jump in. So let's start off with using the series representation of sine of x, okay? And so we have the following infinite sum. This is from n is, starting for our index as n is equal to 0, of -1 to the power n multiplied by x to the power 2n plus 1. Then that's being divided by 2n plus 1 factorial. Now we can actually expand this series out and we get the following. So we have x minus x cubed divided by 3 factorial. Add this with x to the power 5 divided by 5 factorial. Subtract with x to the 7 divided by 7 factorial. And then the series just continues. All right. So now next, let's actually we're actually going to use the infinite sine product, the product representation of sine. And so what that gives, of course, I've actually proved this before, so if you want to look at the proof for that, I have a video of it, so I'll leave that in the link in the description below for you guys to view as well. Formula is defined as the product, x times the infinite product of 1 subtract x squared divided by n squared times pi squared. And now if we were to expand this series out, so of course x is factored out over here. So we have 1, then subtract with x squared pi squared, multiply with 1, subtract x squared divided by 2 squared pi squared, multiply by 1, subtract x squared divided by 3 squared pi squared. And then we could just keep going so on and so forth since this is an infinite product. So now what I'm going to do is we're actually going to set the two equations, the representations equal to each other. So for the left hand side, I'll factor out an x. So we have x multiplied with 1, subtract with x squared divided by 3 factorial. Add this with x to the 4th divided by 5 factorial. Subtract x to the 6th divided by 7 factorial. And keep this going. Okay, and then we set this equal to the representation over here. So let's actually just cut to the next footage so I don't have to see me write this out again. So that's cool. We have the representation here. So obviously what you can see is that we can actually cancel the x's to both sides of the equation. And now next thing what I want to do is we're actually going to use a little fact, and the fact is that the following function, the natural log of 1 subtract x, which if we describe this in terms of an infinite sum, so we have the infinite sum of so this is 0, and then this is x to the power n plus 1, then divided by n plus 1. We expand the terms out, so we have negative, then we have so writing the expression on the inside is a way to group it, so we have x, add this with x squared divided by 2, then add this with x cubed divided by 3, add this with x to the 4th divided by 4, then we just keep going from here. So what I'm going to do, so we have the the logarithm or the natural log of 1 minus x, the series expansion over here. I'm going to now we're going to take the natural log of both sides. So then now once we do this, we have the natural log of 1 subtract, so I'm actually going to group this, and since this is minus, I'll factor out the negative, so we have x squared divided by 3 factorial, or how about this, let's actually calculate the factorials this time. So 3 factorial, that's going to be 6, then subtract with x to the 4th, then divided by 120, add this with x to the 6th divided by 5040, then this is subtract. Yeah, this is subtract, so, well, really, it's, yeah, subtract. Okay, and then that keeps going from there. Then, using the properties of natural logs from over here, so that means we take the sum, so this is equal to the natural log of 1 subtract x squared divided by pi square. Add this with the natural log of 1 subtract x squared divided by 2 square pi square. Add this again with the natural log of 1 subtract x cubed, then divided by 3 square pi square, then keep going so on and so forth. So we take these so I took the natural log of both sides. We just wrote the fact that we have the natural log of 1 minus x gives out this following series expansion over here. So whatever, we have this following similar representation. So for both sides, we're going to use this fact, replace the input for x for what's grouped for each of these, and then we'll continue on further from there. So now let's move on. Okay, so now starting with the left hand side, we'll use this fact. Then if we do all this, so we have a negative, okay, and then now take the natural log with that series expansion. So we plug the input, so we have this following series expansion, plug this back in here. Start with the first term, we have x squared divided by 6, subtract with x to the 4th divided by 120. I'm just going to stop here, so, okay. Now next, we have x squared divided by 2, I'll factor out the 1/2. So this is plus 1/2, then multiply with that input again over here. So x squared divided by 6, subtract x to the 4th divided by 120. Okay, then we add this again, then square. Okay, so that's all we can do for the left hand side. So keep going on with the expansion. We stop here. Now let's actually do the same thing for the right hand side of our expansion. So we do this, so let's see, this is equal to, so negative. Okay, so this one's gonna be a big one. So we have, starting with this input over here for x squared divided by pi squared, just plug this back into this series expansion right here. Let's see, x squared divided by 1 square pi square. Add this with 1/2, multiply by the same thing. Well, now it's square, so now really this is gonna be x to the power 4, then divided by pi to the 4. Plus, stop here. Okay, subtract. We do the same thing again for over here. We're using this input, so we have x squared, then divided by 2 square pi square. Add this with 1/2. Multiply by x to the 4th, then divided by 2 to the power 4 times pi to the power 4. Now, how about I write out one more term? So we have subtract again, then Now, doing this again for x cubed divided by 3x squared pi squared. So let's see, x squared, 3 squared pi squared, then plus 1/2 times, so everything will be to the power 4, x to the power 4, then divided by 3 to the power 4, pi to the power 4, keep going there, subtract, then series goes so on, so forth. Okay, so here's the next step. We're actually going to equate both sides of the equation, specifically the coefficient with x squared to both sides. So anything with just x squared, we're just only going to pay attention to that. So on the left hand side, we're just really focusing on just negative x squared divided by 6, and then everything here is with the x squared, so we have a minus x squared divided by 1 squared pi squared, subtract with x squared divided by 2 squared pi squared, subtract with x cubed or x squared divided by 3 squared pi squared, subtract, the series just keeps going on, so forth. And so now notice that everything has negatives, so I can factor out negative here, there's a negative here, cancel the negative ones on both sides, so now both sides of the equation contains positive terms. So we have now x squared divided by 6, and then that's equal to x squared divided by 1 squared pi squared, add this with x squared divided by 2 squared pi squared, add this with x squared divided by 3 squared pi squared. We just keep going on, so forth, so forth. Yeah, let's actually use this pen again. Okay, so now recall that, no, you know what, since we're going to recall something, I'll put it this way. So now recall that the Riemann zeta function over here, or the infinite sum of the reciprocals of the squares of the natural numbers. So Riemann zeta 2, that says that we expand that series out, and is equal 1 divided by n squared. So we expand this out, we have 1 divided by 1 squared plus 1 divided by 2 squared plus 1 divided by 3 squared, so on and so forth. So now we can just divide x squared to both sides. So that's gone, that's gone, that's gone, that's gone. Keep on going infinitely many times for the x squares, they all cancel. So now we can continue writing the series even more. So now we have 1 divided by 6, and so that's equal to 1 divided by 1 squared pi squared. Add this with 1 divided by 2 squared pi squared. Add this with 1 divided by 3 squared pi squared. Okay, and now the final thing to do is now just multiply pi squared to both sides. Pi squared here, they also cancel from both the numerator and denominator. So pi squared divided by 6 equals 1 divided by 1 squared plus 1 divided by 2 squared, 1 divided by 3 squared, so on and so forth. And look at this. This is exactly the Riemann zeta function, the summation over here, what we're asked for. We just solved the that is equal to pi squared divided by 6. Therefore, we can come to the conclusion that the Riemann zeta of 2, which is equal to the infinite sum, is equal to 1 divided by n squared, is in fact equal to pi squared divided by 6, like so. And there we have it, the final answer, encased in this red marker, like so. All right, so yeah, that's pretty cool if you ask me.